All right, just since I started recording, all I said so far was the solute and solvent definitions, and then we talked about a couple of different heterogeneous mixtures, especially heterogeneous in the phase. And so the solute is going to be the lower amount in solution, and then the solvent is the larger amount. And the only one I know roughly off the top of my head is that air is about 70% nitrogen and about 17% oxygen. And then it's a mixture of other gases there as well. Okay. And so in a solution, the kind of interaction depends on the intermolecular forces between the solute and the solvent, right? And so one general rule of thumb, or the saying we've been saying in the class, is what dissolves what in terms of properties of molecules. What's the phrase that we say in chemistry? It's the same word for both spots, so I'll give you the hint for that. Like dissolves like, right? So we have like dissolves like. And so what that means is that polar things dissolve other polar things, non-polar things dissolve other non-polar things, right? So polar, so example, polar dissolves polar things, and non-polar dissolves other non-polar things. So for example, ionic solids dissolve in water. And so that's like what I showed before with the water molecule surrounding the chlorine atom. That's because the polar H2O surrounds the charged ions. Right, so the polar water molecules, we have a dipole moment in those, they surround the charged ions. So we separate the sodium chloride, which is a neutral molecule, into positive sodium ions and negative chlorine anions. And the water molecules, because it's a very polar molecule, is attracted to the charge on those. Right, so if we look at what that would look like, it'd be sodium plus is a positive charge right here. And then the oxygens from a bunch of water molecules would probably be facing the sodium atom. And does anyone have any idea why it would be in this orientation as opposed to another orientation of water molecules around the sodium atom?
Because the hydrogen wants to be on the outside.
Hydrogen wants to be on the outside, so why would the hydrogen want to be away from the positively charged sodium? Why do you think?
Because the oxygen is negatively.
Yeah, the oxygen has a partial negative on it, like this, right? So because it has the partially negative charge, it's attracted to the positive charge around the sodium, right? And the hydrogens are all partially positive. So these are all going to be partially positive. That side of the molecule is partially positive. So they're going to stay away from the sodium ion.
Because all the lone pairs, right?
Yep, so all the lone pairs on the oxygen, right? If we were to draw the dipole moment, it would be from positive to negative. This would be what the dipole would look like, right? So you always have the arrow going from positive to negative. And you want to opposite charges attract each other, so that's why we would get this kind of structure around the sodium ion, right? And so like dissolves like, that just means things with similar chemical properties dissolve other things with similar chemical properties. So you can imagine if you have water and oil, water has hydrogen bonding, London dispersion forces, and dipole-dipole interactions. Oil just has London dispersion forces. So because water can form much stronger bonds with other water molecules, it will stay to other water molecules. It will stay away from the oil molecules. So that's why those two things will separate from each other. Nonpolar molecules such as oil and grease also dissolve in nonpolar solvents. All right, so that'd be something like kerosene, hexanes, even sometimes like acetone. Those things will dissolve nonpolar molecules, right? And so if you only have London dispersion forces, then you'll be attracted to other things with only London dispersion forces, right? You can't form strong bonds with water molecules, so you stay separate from those things. Okay. So if we look at a couple liquid mixtures here, we have water and then methylene, which is CH2Cl2, right there. And those separate because they have different physical properties, right? So this is nonpolar, water is polar, and so they separate based off of that. How do you know which one is going to be on the top and which one's on the bottom? Yeah, the more dense thing is going to be on the bottom. So this is going to be more dense on the bottom in this case. And you can always determine what is the more or dense liquid based off of where it is, if they separate, right? And so if we look at I2, would you say iodide is more, or let's say all the clear solutions here are water. So this is H2O, H2O. Would I2 be more or less dense than water? More dense because it's on the bottom. And then why does it separate from water? Yep, this is going to be polar, and so it's the same idea here. This is going to be polar, and I2 is nonpolar, so they separate. I2 goes to the bottom because it's less dense. Let's say that this solution here was instead formaldehyde. Actually, let's say this is going to be liquid methane, CH4. Right, so this is methane. If I gave you a picture of a test tube like this, and I said, well, just based off the test tube, would you say that methane is going to be polar or nonpolar? What would you guys say? It'll be nonpolar, and you would know that because they're not mixing. They separated from each other, so they have different chemical properties or physical properties. And then would it be less or more dense than nickel nitrate? It would be more dense because it's on the bottom, right? So it would be more dense. So again, we get this mixture or separation based off of intermolecular forces. So intermolecular force is going to be one of those things that doesn't go away for the rest of the semester because this stays with us through organic chemistry. This will be a type of separation you see a lot in organic chemistry, and you can actually take advantage of things separating like this. And so you can do some pretty cool experiments by separating the layers, right? So you can drain one layer and keep one layer, and you keep whatever product you have there. Or if one thing is more attracted to one of the liquids, and let's say it's originally in water, but you want it in your dichloromethylene, you put it together, you mix them, so eventually with the molecule that you want to separate from the water will move into the dichloromethylene, and then you can then extract that layer and get your product isolated from water in that case. Okay.
So is it typical for non-polar to be more dense, or is that just a coincidence?
That's just a coincidence. It doesn't really have to do with the polarity of the molecule. Generally, once you get to very, very large molecules, right, they'll separate from water because if you get to extremely long carbon chains, that's going to be more dense than water in any case because you have larger molecules, right? If you have the same volume or per density of them, which in most cases the density will be relatively the same for liquid molecules, right? Liquids are going to be mostly identical, not densities, but they'll have compactness, right? Those molecules are generally going to be as close to each other as other liquids, right? Because gases are really far apart. Liquids are close together, but they can still move, and then solids are close together and they're held in place. Mm-hmm.
For solids, don't they vibrate though?
Yeah, everything vibrates, right? So the only way things don't vibrate is if you have absolute zero temperature, which doesn't exist in the universe. If it did, then we'd all die. So there's always going to be motion, slight motion, right? So even in solids, things are vibrating like this all the time. Yep. And then in liquids, it's even more. They're moving and vibrating. So they have, we'd say, technically more degrees of freedom whenever you go from one state of matter to the other. Okay. And so the way we classify solutions, or we kind of quantify the amount of something or the amount of solute dissolved in a certain amount of solution, is called the concentration. And you guys are probably familiar with this word when you think about like juice from concentrate, right? That means you're going to have a very concentrated solution that you then dilute. And so concentration is just the term to describe how much solute is in the solution, right? So this is going to the amount of solute over the amount of solution. Right, so I'm using the general term amount here because there are different ways that we can define the concentration of a solution. And so the three types, that are probably around 4 types, can be separated into 2 categories. It'll be either the mass or volume percent or the molarity. So like 1, 2, and 3. In each mass, you can have a mass to mass percent concentration, a mass to volume percent concentration, and a volume to volume percent concentration. Molarity, this is going to be the most prominent in chemistry. This is the concentration we use in chemistry most of the time. And then these ones are more important outside chemistry. Right, so you'll see that a lot of times in nutrition and in the health field, you'll see the percent concentrations.
Is the mass also percent?
Yeah, so it would be mass or volume percent. And so the 3 ways you can have a combination between these two is the mass to mass percent, the mass to volume percent, we'll talk about each of them, and then the volume to volume percent. And you see sometimes one is used over the other because just what are you mixing? If you're mixing 2 liquids together, sometimes it's easy to find volume to volume percent. If you're putting a solid in a liquid, then it's easier to define a mass to volume percent. Mass to mass, I'm not really sure off the top of my head where people actually use that. All right, so a mass to mass percent solution is defined as the mass of the solute divided by the mass of the solution, right? So we have the percent m dash m in parentheses. This is basically how we define the unit of concentration, right? So the same way we put grams or something represented by lowercase g, when you do a percent m and then in parentheses m dash m, that means it's a mass percent concentration. And so it's the mass of the solute divided by the mass of the solution times 100, right? So that's how we get the percentage. And then if we're given a percent mass to mass, what this is also can be defined as, or when we turn this into a conversion factor, it'll be the mass of solute per 100 grams of solution. So if you're given the percent mass to mass value. So what I mean by that is if you have a 5% mass to mass concentration, that means you have 5 grams of solute over 100 grams of solution. And so one thing to keep in mind here, especially with these percent concentrations, is that it says the mass of solution, right? Sometimes I'll abbreviate solution as SOLN. And the mass of the solution, right? This is the mass of the final mixture of everything. This is the mass of solute plus the mass of solvent, right? So it's easy to get this part confused because sometimes if you're mixing 2 solutions together, you think I'm adding 100 grams of this to 150 grams of my solute, and then you want to take 50 divided by 100 in that case, when really the mass to mass concentration is going to be 50 divided by 150 because you need to add together the mass of the solute and the mass of the solvent in that case. Okay, any questions on that? All right, so the next and more, I'd say more common concentration unit is the mass to volume percent. And so this is defined as the mass of the solute divided by the volume of solution, right? So the volume of solution. And so the same way last time, we had to be careful about the mass of solution instead of using the mass of the solvent. Here you just want to keep in mind that keep writing M, the volume of solution is equal to the volume of solvent plus the volume of solute. Right, so the volume of the solution is going to be the volume of both of those. So if you're mixing two liquids together to get a mass to volume percent, you need to be aware of that. Generally, if you're mixing a solid and a liquid together, the mass of the solvent will be the mass of the solution. So when mixing a solid in liquid, the volume of solvent generally equals the volume of solution. Right, so those will generally be the same, right? It makes sense if you have table salt, you dissolve it in water, the volume of the water usually doesn't change a whole lot. There is a slight volume change when you mix two things together, but really it doesn't change a whole lot. And if we're given a percent mass to volume concentration, then the percent mass to volume is equal to the grams of solute per 100 milliliters of solution. So if you have a 7.2% mass to volume, what would be the ratio we would have for that? It would be 7.2 grams of solute per 100 milliliters of solution. Right, so that's how we use the value of the concentration there. All right, any questions on that? Good. All right. Okay, and then the last concentration is the volume to volume percent, right? And so again, when we're careful here, the volume of solution is equal to the volume of solute plus the volume of solvent. And here, most of the time, you'll be mixing two liquids together. This is usually when mixing two liquids. You could also do it for gases because they have a defined volume if they're in a container, but I'm not gonna give you guys anything with gases. And so if you're given a percent volume to volume, this is going to be the volume of solute over the volume of solution sorry, the 100 milliliters of, per 100 milliliters of solution. Milliliters of solution, right? So an example of this is if we had a concentration of 22.3% volume to volume solution, that would be 22.3 milliliters of solute per 100 milliliters of solution. Jeff?
So in a situation where the, what's it called, like milliliters and milliliters aren't matching, you'd have to do a conversion to get.
Yeah, so if you, for example, didn't have the solute in milliliters, you had it in liters or something like that, then you'd have to convert that to milliliters to get the percentages to work out. If you do everything in terms of liters, it still will technically work out, right? Because you're changing the numerator and the denominator by exactly the same amount, by the same factor. But when you're doing either writing out a percent value as a ratio there, then you want to make sure they have the same units. Or if you're finding the percent concentration, you need to make sure those have the same units, right? Because this unit right here is technically, should not have units of volume or mass in it for the percent concentrations. Those should cancel out because this is a percentage value. Yeah, conversion is basically going to haunt you for the rest of the semester and probably the rest of your life, depending on what field you want to go into. But like I said, a lot of times conversions, you guys do that all the time when you go shopping, right? You have $20 and there's a sale, 3 for $15 or something. You just want to know how many shirts you can buy. You do unit conversions all the time in your head. It's just, it's more intuitive than doing things and, we're combining things with chemistry, which we already are like, I don't know how I feel about that. So we have more of an aversion to unit conversions in this case. Once we get to, so in 2 weeks from now, everything we'll be talking about will be less about unit conversions are mostly going to go away in organic and biochemistry. It'll be less math and more understanding reactions and structures of molecules. Gen Chem has a lot of math in it, instrumentation and units, and then we're not going to talk about gases a whole lot. We'll probably talk about gases a little bit on Thursday, but that's even more algebra associated with that. But you guys, I'm not going to examine you guys on gases. I'm just going to introduce it so you guys will have said you've seen it before. Okay, any questions on any of these concentrations? All right, so here we have a problem. So it says, what is the mass percent concentration of sodium hydroxide solution that is made by dissolving 30.0 grams of sodium hydroxide in 120 grams of water, right? So this is a mass to mass concentration problem. So you're trying to find the mass concentration, right? This is what we want. We want the mass percentage concentration, which means that the formula that we're going to use is that this is going to be equal to the mass of solute divided by the mass of solution times 100. All right, so that's how we're going to get this value here. And so what is the mass of solute in this case? How do we know which one is the solute and which one is the solvent? It isn't necessarily which one's heavier, it's which one we have more of, right? So we have an amount of both of these, which are the grams. So the 30 grams is less than 120, so this is going to be the solute in this case, right? And so the mass of solute is 30.0 grams, and then we divide that by the mass of the solution, right? So what's the mass of the solution here? Yep. This is going to be our solvent, right? And then the mass of solution is equal to 30.0 grams plus 120 grams, right? Because the mass of the total solution in the end is 120 plus 30, it's going to be 150. So this is equal to 150.0 grams. This would be 150.0 grams. And we multiply that by 100. And so this will be 0.2 times 100, and we'll get 20% mass to mass concentration. All right, so the thing to be aware of here is that they give you the mass of the solvent and the mass of the solute. You just have to know that the mass of the solution is the addition of those two. And then you take the mass of the solute divided by the mass of the solution times 100, and that gives you the mass to mass concentration. Jeff?
So in this one, the solute and the solvent have to be the same thing for the percentage. Like, say there was a different solvent and solute, like you're dissolving two different things.
Yeah, so you don't worry about the specific units, like you wouldn't, grams of sodium hydroxide, you're just specifying the grams of the solute in this case. So it's the unit itself isn't grams sodium hydroxide, it's just grams in this case. Because we're just looking at the relative mass differences, not like, for example, when we look at, doing conversions with chemical quantities and chemical equations, the grams, the unit, what molecule you're looking at is important. For concentrations, it's just how much of that stuff is in the total stuff. You're not as worried about which molecule is which, as long as you identify solute and then solution and solvent. Okay. All right, so here's mass to volume percentage. So what is the mass percent volume of a solution prepared by dissolving 5.0 grams of potassium iodide to give a final volume of 250 milliliters, right? So here we have a volume and a mass, and then we have to plug it into our formula, which is going to be the mass to volume. Concentration is equal to the mass in grams of solute over the volume of solution times 100. And the volume of solution is given in milliliters in this case. Okay, so why don't you guys find the mass to volume percentage?